Okay, welcome back, folks. Good morning again. This is Dr. Adam Pease and Viru Mirji here from WinWire. We're going to talk about the fourth segment of our talk on AI ontology for health and data sciences. And last time we had a very interesting discussion about, the different kind of definitions and the uses of ontology. And I'm hoping today we can go a little bit further. So, Dr. Adam, would you like to start with kind of a recurse, like a re review of what we talked last?
Right, so last time I mentioned the SUMO and also the Sigma system, which are both these open source resources for reuse of a large ontology library that's very expressive, and then also a tool set that helps you extend that library.
Excellent. So today we'll talk a little bit about automation here. Would you like to talk a little bit about how this thing comes together?
Yeah, so one of the key things, really a key problem in doing metadata development is that a lot of the metadata, a lot of the definitions, a lot of the meaning that one has been able to state about data in the past is not really computable. And so a very small amount of metadata, say one developer can kind of keep all the meanings in his or her head and make sure they're all consistent. But the reality of modern data sets is not only do they have lots of instances, they have lots of rows or tables or columns, if you can think of it that way. And all of those tables or columns need definitions. And if there are a lot of them, it soon becomes impossible for a single developer to keep all that information in his or her head and know that the intended definitions are actually consistent with one another. And if they're not consistent, if things aren't used in a consistent way, and especially if you have a big or distributed team where it isn't just one person trying to keep the whole arrangement in one brain, but rather multiple people in different places trying to communicate and keep all of their definitions in harmony, you've got a very hard problem. You need some automation, and if you're going to do this with have some automation, you can't just have the definitions in a human natural language like English. And so that's why we define everything formally in mathematics. And it's why we have a recourse to automation. We use a technology called theorem proving that can work with these formally stated definitions. And really all you have to do is press a button and say to the theorem prover, tell me, is this theory consistent or not? And it will tell you. So we do this sort of work daily with SUMO. In order to determine whether everything that I've said, as well as everything new, the handful of axioms that I added, handful of statements I added yesterday, are they really consistent with everything I said over the past 20 years? And that's tremendously powerful. If you've got a traditional data warehouse, an additional traditional way of representing metadata, you don't have that possibility. You can't have the computer work on all of your English definitions, even if you have them, and tell you whether all those definitions are consistent. But if you've done that in math, the computer can tell you. That's really powerful.
Excellent, excellent. Yeah, this is great theorem proving as a technique. Now, what about matching, ontology matching?
Yeah, the fact is, of course, that most systems don't have these kinds of definitions. So we've got to have tools and processes for bringing in other systems into this data warehouse, the set of definitions that are in SUMO. So we've done a lot of this. We've done especially a lot of it with giant fact bases like Gerard de Mello and Fabien Souchenek's work on Yago, which is a big fact base. It's used a lot in the linked data community. But in that community, they don't do a lot with definitions. They sort of make their matches and kind of hope or trust that they've matched things correctly. We don't make that assumption in SUMO. We define things precisely, and we have theorem provers that can check for consistency. We have a process for trying to link to lots of other projects, and we've done some academic publication about that that people might be interested in.
Yep, yeah, very good to know. So, how much time, does it take for picking up these technologies, these tools?
Right, and for somebody that's not already familiar with mathematical logic, this might seem esoteric or researchy or scary, but it's actually not. It's really just another programming language, albeit a different programming language. So, if you're already a Python programmer, it's going to be like learning a new and rather different programming language, but it can be done. And so I've done this many, many times, both at the university level and also in corporate seminars. There's textbook for it, and it takes really about 5 days of training, and I can get people up to the speed where they're contributing meaningfully to the standard. And just like a programming language, it's going to take some time to develop real fluency, real facility with this material. That takes practice, just like any programming language, but I can get people started in about a week.
Excellent. And do you think the level of expertise matters? The number of years of experience. What are your thoughts about that?
It's really interesting that I've found that the most important thing for this is an interest or a passion for things like language and linguistics, a little bit of the sense of being a programmer, being happy with writing code and dotting your I's and crossing your T's, that the sort of thing that programmers have to be interested in and not frustrated by. But really the most important thing is an open mind. I have a lot of luck with people that are, say, fresh out of college, or even in several cases fresh out of high school, learning this material. So it's certainly takes some sophistication, but it doesn't take a lot of background. It mostly just takes a certain degree of aptitude, interest, and humility, and people can learn this stuff. It's really just, again, like any other programming language.
Excellent. Yeah, what I'm showing on the screen is a quick snippet of viruses. Since we're talking about coronavirus and healthcare, I thought we'll show the Sigma knowledge engineering environment that you've set up, and kind of a quick review of all the definitions around viruses and what derivations come out of that. So very interesting. Thank you for your time around this. Tell me.
Yeah, thank you.
Yeah. Anything else, Dr. Adam?
Well, maybe I could just very briefly say that this is a great illustration of some of the value of a library. This stuff that we did on viruses, we did 20 years ago. I mean, long before coronavirus was top of mind. But some of these concepts and definitions for things like being an RNA virus or single-stranded virus that is relevant to today's understanding of the mechanisms of a coronavirus, or things that we defined a very long time ago. And so elaborating these, we don't have to start elaborating these notions specific to today's crisis. We don't have to recreate this stuff from scratch. We created it already 20 years ago, and that's a really valuable resource.
Excellent. Thank you for that. Thanks for your time. I'm going to stop sharing right now, and I really appreciate the explanation behind how to use ontology. Glad that we can keep talking about this and how it applies to health informatics as well as data sciences in general. So appreciate the time. Thank you.
Thank you. Thank you. This has been fun.